Hello, everyone, and welcome to week number 8, lecture number 15 overall. We've just started this class. I didn't miss anything by talking before I started recording. So this is the very beginning of class, and that is my story, and I'm sticking to it. Um, so here we have a lovely page, which has already been loaded. It's been there for a long time because I was preparing and stuff. And it's about conditions for inference and when you're allowed to use inference. It'll be a little shorter. This one will upload a little faster. So the three conditions, I'm gonna say them for the first time because I haven't said them yet, is that one, must come from a simple random sample with no practical difficulty. The population must be large compared to the size of the sample. It has to come from a normal distribution. And what we're looking for mu, but we don't know it obviously, but we do know sigma. Okay. I don't know what you're talking about. Okay. I don't know what you're saying there. But this is obviously the beginning of class. So these are the conditions upon which I'm allowed to use the formulas for the confidence interval, which is x bar plus or minus z star sigma over the square root of n, and the formulas that Crunchit or other Google calculators will use for the null hypothesis versus the alternative hypotheses. These also are predicated under the assumption that all of these properties hold. If they do not, then you can't use them. So either greater than, less than, or not equal to mu naught, the three possibilities. Okay, it's only when these three hold that holds and that holds. If they don't, then beware, because your conclusion might not be valid. Okay, so let's do an example where I saw a good example earlier.
Professor,
Yes,
those three requirements has to happen in order for us to do what?
in order to use the formulas that we've been developing, or the Google calculators formulas that will do it for us, for confidence intervals and for hypothesis testing. The first equation, which I have written down, I can undo probably. Yeah, there we go. I'll give you a second to write them because it hasn't been on the page very long. So, because we just started class. So it's understandable if you haven't had enough time to write the equation down. I get that. It's not like this has been there for a while already. Just saying. What? Terrible liar. Crazy talk. So do you have it now? Okay. Me sarcastic? What? Never. All right. So I had a lovely example, but it must come from a different section because I don't see it here. But let's address. So someone said a question here. It says, these three requirements for, yes, it has to hit these three requirements for our current formulas for confidence intervals and hypothesis testing. Okay. As we go on through the book, we will have other formulas for other scenarios, and some of these conditions will not hold any longer. For example, we're going to have, what do you do if you don't know sigma? And we're going to come up with a different confidence interval formula that uses what's called the T star instead of Z star. If you remember on Crunchit, every time we did Crunchit, we had to pick Z or T. So we've been using Z because we've always known sigma, but if you don't use T, so we're going to derive all these formulas for these different situations. So what are those, that condition number one that said there's no non-response or practical difficulties? What does that mean, practical difficulties? So It says there's no simple rule for deciding when you can act as if a sample is an SRS. That's first of all. Okay. In problems in a math class, it'll say it's an SRS. Assume it's an SRS. Presume it's an SRS. Suppose it's an SNS. Whatever word they want to use. But in real life, the question is, how do you really know if it's an SRS? If condition number one is you can only use these formulas if it's an SRS, how do you know if it's an SRS? So there's no simple rule. Okay, you just have to kind of sometimes use common sense. Remember again what an SRS is, because we went over this in a previous lecture, not like before today or anything like that. An SRS is a sample, simple random sample. An SRS is a sample where you pick a certain size from the population. So if the population has a million people and you pick 50 of them, you're choosing 50, but you're choosing 50 in a very specific way. It's not every 50th name in the alphabet. That's a systematic sample. It's got a system behind it. It's not stratified, where you split up the population to men and women and pick 25 of each. It's not a cluster, where you separate the pieces and take some of the pieces. A simple random sample is very specific. Any 50 people in the population are just as likely to be picked as any other 50 people in the population. In other words, there is no bias or tendency for some to be picked over anyone else. That's a simple random sample. So when you're given a problem, you have to look at the situation and decide whether or not it was constructed in that way. Okay? Um, by common sense. Just ask yourself. Like if I say, um, there's 50 people in a room and you want to pick a simple random sample of 5 of them. So you put everyone's name in a hat, swish around the hat, and pull out 5 names. Is that a simple random sample? Are any 5 people as likely to be picked as any other 5 people in that scenario? Yes. They didn't say it was a simple random sample, but it is a simple random sample because it satisfies the condition of being a simple random sample. That's what it comes down to. If it satisfies the condition, it's an SRS. If it does not, it's not. If I'm interested in people's voting opinions in Los Angeles, so I call 100 random numbers in Los Angeles. Is that a simple random sample of all voters in Los Angeles? No, right? It's not true that any 100 voters in LA are likely to be picked. First of all, even kids these days have phones, so they can't all be of voting age. And then there's people who don't have phones that are people with no phones are of voting age. So not every group of 50 people or 100, whatever number I picked, is as likely to be chosen as any other group. Therefore, that is not a simple random sample. They didn't tell me it wasn't a simple random sample. I just have to know what an SRS is and decide on my own that it's not a simple random sample. Okay. But what are some practical problems that we don't want? We hate non-response. We don't want people to say, don't call here, even though that's exactly what I do every time I get one of them, because I don't got time for that shit. So non-response or dropouts, people who just leave an experiment in the middle because they just don't care anymore. Okay. Um, Voluntary response surveys, there's no cure for that. I mean, those are just the worst, or uncontrolled experiments. You can't fix that. If you have a voluntary response survey, bam, it is out. Don't ever infer anything from a voluntary response survey. Okay, because people who answer voluntary response surveys are people who are passionate about the subject. That's not the overall population. It's a very small niche or niche. Is it niche or niche? Anyone know? Niche? Okay, you can't type it. You have to say it.
It's niche.
It's niche. It's such a cool word, niche. I love it. Even though I've always said niche, but whatever. Okay, so what else we got here? Niche. I love that. So let's look at specific cautions about confidence intervals. This is the big one. We know the confidence interval is x bar, the sample mean, plus or minus z star sigma over the square root of n. So this plus or minus part, this thing at the end, this z star sigma over the square root of n, this guy here, this guy is called the margin of error, which we'll just use the letter n to denote. Okay, the margin of error is z star sigma over the square root of n. And anytime you do a confidence interval, you get your value plus or minus a little bit, so you have your confidence interval. The question is, does that confidence interval truly represent the margin of error? Does the margin of error cover all possible errors? And the answer is no. The margin of error covers only errors that come from samples. Any other situation like practical difficulties such as under coverage, non-response, the margin of error does not take those into account. So when you see a survey, like for example, number 4 here, what's your weight? It says a 2015 Gallup poll asked a national random sample, so it is a random sample, of 389 adult women to state their current weight. Now, it's not a true simple random sample because the Gallup poll cannot reach every single adult woman in America, and therefore it's not truly an SRS. However, we will treat these data as an SRS. In other words, even though we can't get everyone, the ones that you can't get should not really be any different from the ones that you can get. So we're going to treat it as an SRS. Okay? So it's a simple random sample of 398 adult women to state their current weight. The mean weight in the sample was x bar equal 155. It's normal and sigma is 35. So all the conditions that we want are here, or at least the mathematical conditions. So part A, give a 95% confidence interval for the mean weight of adult women based on these data. What would my 95% confidence interval be? Let's write it out. What's the first part? Not everyone at once now. Anyone?
Is it the decimal? So would it be like 1.960?
Well, that might be Z
For 95?
star, but I want the whole thing. What's X bar? Let's start from the beginning. What's X bar?
155.
155.
And then plus or minus.
Plus or minus.
And then 1.96. And then 35 over the square root of 398.
Wonderful. What's the Q again? What's the Q again? Well, Q is a letter in the alphabet. Usually precedes the letter U, but not always. So it's just one of 26 letters.
Wait, how do we get 1.96 again as the Z star?
Oh, she meant question. I never would have guessed that. But anyways, we get 1.96 because they told me that we're having 95% confidence interval, and 95% confidence always is 1.96.
On the Z table, right?
On you can get it from the Z table, but there was a table last chapter, maybe 2 chapters ago. 90% Z star is 1.645. 95% Z star is 1.96. 99% Z star is 2. I think it was 2.26 or something. Oh, someone's writing it. Oh, awesome. Let's see. She said, was that right? 2.576. Okay. So those are just facts. Facts. Okay. Anytime you have a Anytime you have a Z table, Z star, those numbers come directly from the confidence interval. Anyways, do you trust that the interval that you computed in part A is the true 95% confidence interval for the mean weight of all US adult women? Why or why not? Do you think that what the math gave us is accurate? Why not? What's wrong with the math? What practical difficulty can exist in this scenario? I mean, 398, it's a pretty large size sample. Some people probably lied. I love it. Well, there is non-response and undercoverage. It's always possible. That's true. But I think the biggest issue is that people, for whatever reason, lie about their weight. I don't know why someone would do that. I've been accumulating weight for so long. I'm very proud of my weight. So why would I want to, pretend it's less than it actually is? I don't get that. But what do I know? So this is probably not valid. I don't know so much about non-response and undercoverage because are people who might not be reachable be less or more likely to be overweight? I don't know. It's a good question. You might say, well, people who can't be reached might be homeless, and homeless people are in general thinner, and therefore not by choice, but just by lack of nutrition, might be less heavy than people who are. But actually, I read a study once that during the Depression, or maybe it was, I think it was one out of four kids was overweight in the Depression. Maybe it was even more than that. I don't remember because it was about what they ate, not so much how much they ate. Certain foods were just more prone to putting on weight than others. Usually the good stuff, the stuff that everyone likes, like orange creamsicle and stuff. Anyway, let's move on because we know everyone loves orange creamsicle. No one does not. Let's see what else we have here. Let's do number 7. Sydney, there's a line, Sydney. There's a line. You just crossed it. You don't like orange creamsicles? I'm fighting words. Just be aware of that. I'm in a good place now. I'm gonna let it go. But okay. All right, number 7. A July 2015 Gallup poll asked a national sample of 1,009. What a huge amount. Adults aged 18 and over if they actively avoided drinking soda or pop. Of those sampled, 61% indicated that they do so. Gallup announced the poll's margin of error for 95% confidence as plus or minus 4 percentage points. Which of the following sources of error are included in this margin of error? So read the question, or at least read the answers, and answer whether or not you think it was A, B, or C. A, B, or C. Excuse me, sorry. A, B, or C. All right, we got an A. We got one A so far. Couldn't it be both A and B? No, the answer is either A, B, or C. But if you want to say A or B, I will accept that as a half answer. Oh, I got an A or C. I got an A, got a B, another B, another A or C. A. Any I don't knows? IDK? Any IHNFCs? A or C? All right. So the answer, Danitza, is C. Because remember what we said earlier, the margin of error does not cover all errors. It covers only random sampling errors. A is not a random sampling error. A is an error based upon your methodology. Okay, you can't reach everyone under coverage. B, errors based upon non-response. Those are not random errors. Those are errors coming from the practical situation. C, there's always a chance variation in the random selection of telephone numbers. That's exactly what margin of error is all about. Not every sample is going to be the same, and therefore you're going to have different values. Sorry, can you repeat why it's not A again? A is not an error that comes from the math. It's an error that comes from the methodology. You did a experiment where you're calling people, but you're not being able to reach everyone. That's not a random error situation. That's the bad approach on your side. That's not a margin of error thing. Now, if the margin of error is computed, does not actually take everything into account. If I did take everything into account, do you think the margin of error will be bigger or smaller? If I did take everything into account, do you think the margin of error will be bigger or smaller? That's two smallers. Do we have any biggers? Bigger because you're accounting for more possible goofs. Interesting term, goofs. But yes, it is bigger. That is the right answer. It is bigger because you are accounting, well, because the margin of error is kind of like, here's my value, but because there's some uncertainty in the world, I'm going to actually extend it outwards a bit to include this. Well, if there's even more uncertainty, that should make it go even further to account for, right? Every additional inclusion or every additional possibility of error should make the margin of error get wider. So the answer would be wider, not smaller. So when you actually read a Gallup poll and it says it's 61% plus or minus 4, you're like, okay, that made this between 57 and 65. In reality, it's bigger than that. It's impossible to say exactly by how much, but it is bigger. Okay? Does that make sense? So, yes?
Is C pretty much saying that there is little variability and that's why that there was the source of error?
No. What C is saying is the margin of error only comes about because of the fact that every sample is going to have technically a different answer because they're all samples. So there's always going to be a random variation that comes from different samples. The margin of error only accounts for that. It doesn't account for anything else that might play a role. So if you did want to account for everything else, just go further out. How much? Well, that's beyond my pay grade. I don't even know if there's math for that, but I certainly don't know the math for that.
Thank you.
Okay. So let's go now about cautions about significance tests. We did a little bit about confidence intervals and now about significance tests. And the first one is that whenever you do a significance test, there's always the cutoff point, and the cutoff point is the value at which, if your p-value is smaller, you reject the null hypothesis, and if the p-value is not smaller, then you do not reject the null hypothesis. And the question is, how small a p-value do you take? So the general rule of thumb is that if they don't give it to you, then you assume it's 5%. But is 5% always appropriate? And the answer is no. Suppose somebody were trying to convince you that you're wrong about something, mathematically. I guess an example would be the following. What is the temperature of a healthy adult here on Earth? What is generally considered to be the perfect temperature for a healthy adult here on Earth? So it's 98.6, right? 98.6, 96.8? No, 98.6, right? I think that's it, 98.6. I don't even know anymore. But I believe that's correct, 98.6 degrees. Suppose somebody came along and said, you know what? It's not 98.6, it's something else. What would you say? If someone came along and said, you know what, it's, yeah, everything that you've been brought up to believe is just wrong. It's really not 98.6 at all. Show me the Carfax. Basically, prove it, right? Convince me. What's that from? Convince me. Oh, of course. The Usual Suspects, right? You guys familiar with the movie The Usual Suspects? No? Nobody? Oh my God. It's only one of the, oh my God. It is only one of the greatest movies of all time. Oh. Do I gotta give extra credit for watching this now? I can't, because it's like an R-rated movie and whatnot, and it could offend people, so I can't do that. But my God, it is just awesome. And yes, I know that one of the actors is not really considered well liked anymore for certain off-screen proclivities of his. But if you can get past that, it's Kevin Spacey. So Kevin Spacey is he might not be the paragon of virtue, but in terms of this, his acting is still first rate. I mean, the movie is still amazing. It's called The Usual Suspects, and if you've never seen it, I actually give you permission right now to pause this. No, Bill Cosby, hey, that's all he can do. No, this is a real actor. You should probably pause this lecture just to watch the trailer for Unusual Suspects, just to appreciate the. Yes, that's the one. But don't read up on it. Don't stop. Don't click that link. Do not click that link. Okay? It'll reveal things about the movie that you do not want to know going in. Trust me on this one. Trust me on this one. It will ruin your life. Sorry. Unclick. Oh, kids these days. But it is an amazing movie if you like violence. Of course, if you don't like violence, stay away. It's very violent. But if you like violence, it's just amazing. Great acting. It's not gory. It's violent, but it's not gory. Okay, it's not a horror movie or anything like that. Not gory in any way, but it is violent. I will. Blood. I mean, there's killing and stuff, but not really blood. It's not that kind of movie. But anyway, if you don't like it, turn it off. You don't have to watch it more than 2 hours. Just don't watch 2 hours and 1 minute. Anyways, back to math, guys. Come on, focus. So, what's not working? I don't know. Whatever. Okay. Let's get back to math. Just watch it over the weekend. Skip your statistics homework and watch it. You'll be better off in life for having done that. So, how small a p is convincing? So, if you come along and say, okay, I don't believe the temperature, the average normal temperature is really 98.6 degrees. You have to convince me otherwise. I need really strong, convincing evidence to reject something that I've been believing my entire life. In that case, a p-value of 5% just might not be enough. And you might got to go 1% or even less than that. In physics, for example, uh, um, when they do studies to find new fundamental particles in nature, their p-values are extremely small. You got to convince the entire scientific community that your data is accurate and it's not just a freak chance, and that requires a very small p-value. So the point is that there's not one and only one value, and it has to be done on a case-by-case basis. And again, the real question is, what are the consequences of rejecting the null hypothesis? If you take a larger cutoff, like 5%, so your alpha is 0.05. So anything, if any p-value less than alpha, I'm going to reject. Then you're going to reject 1 in 20, right? Or assuming you're supposed to, anything less than a 1 in 20 chance you're going to reject. But what if rejecting means hiring a new staff, calibrating your equipment, rewriting your code, hiring new staff, training your, I mean, who knows what the consequences of rejecting the null hypothesis can be? And if the consequences are severe, you want to make sure that you do not make a mistake. And again, in that case, you might take a smaller alpha than you normally would, maybe 1%, maybe a tenth of a percent, whatever the case is, so that you don't accidentally do something which is going to cause you to lose a lot of money in the long run if you didn't really have to. Okay, so in this class, 5% is the generally acknowledged value, but just be aware in real life, it's not always going to be that. It depends on the situation. Okay. Okay, so let's now move on to a little bit of math. Planning studies. Okay, so we've already established that the margin of error, I think I have the wrong book. The error. Yeah, so I don't think that the book is necessarily page by page the same as the one that I'm working with. I think we had that issue earlier in the book, but it is chapter 18. So but you're saying it's 22. I mean, this is the book, right? This is the one, right? Oh yeah, so this one is 22. Interesting. Okay, well, 1 second. Hold on. Okay, that's fine. There's a significant overlap, but you're right. What we're using here, which I thought was this, because when I go to the home page, the basic practice. Oh, well, never mind. Never mind. It is 22, but it covers the same material. So hold on a second. All right. Well, that changes a bit, but we will finish this. Shit. Okay. Okay. that does change things. That does change things. But not that much. Okay, the 15, 16, 17 that we did is all the same. So that's not an issue. What I'm going to do, instead of using this, I'm going to stop sharing for a second. Hold on. Hold on. I am going to do the following. I don't know how to. How do I? Let's do it like this. Okay. Back to sharing. Thank you for pointing that out. I apologize. Okay. So I'm just going to write on this thing here. Okay. So then what we're going to do now is not, I mean, what we just did is fine, and you're going to need to know it anyways. Just, I did it a little out of order. What we're going to do now is I'm going to list for you various various confidence interval formulas for various cases. So we already have the first case, which is X bar plus or minus Z star sigma over the square root of n. What's someone to say? So annoying. So this is not chapter 22. This is actually in the book. We're going to go in order. So we just did 16 and 17. I'm writing down the formula right now for what we did in 16. So if you want to know the page, go to page number, if you're following along at home, go to page number 356. And it is I thought this was equal to our book, and it's not, so I apologize for that. But luckily, it wasn't significantly a significant deviation from the book. So it's easily fixed. But again, I'm sorry. So we have here is p hat plus or minus Z star square roots of p hats 1 oh, this is horrible. I can't write like this. Okay. So we have p hat plus or minus a Z star, the square root of p hat 1 minus p hat over n. The first example, no, this is 16. This is chapter 16, okay, which we, how do I move this? Okay, 16, okay. These are two different confidence interval formulas in chapter 16, okay, for two different situations. This one is when we're looking for the mean of a distribution. We're looking for the average. We want to know the mean mu. Okay, we don't know mu, so we take a sample of size n. We know the underlying sigma, the underlying population standard deviation. We have our confidence level, which gives us our Z star. We take our sample, it gives us our sample mean, and we have a formula for the confidence interval for that situation. The second example is when we're looking for a proportion. For example, the Lakers, as we all know, hopefully, or I don't actually care if you know or not, or you might not like basketball. but the Lakers just won the finals, and someone might be interested in knowing what Anthony Davis's free throw shooting percentage was in general. He shot very well in the finals, was like 40 for 41 or something like that. He had a very high free throw shooting percentage over the course of the finals. But yeah, maybe it's 85%. We want to know. Suppose we don't know what it is. We want to know what it is. So what do? We say, okay, Anthony, why don't you go and shoot 100 shots? And what we're going to do is we're going to base our confidence interval after your performance. So we're looking for the true proportion P. We obviously don't know the true proportion P. If we did, we would just write it. But what I have instead is the sample proportion P hat. This is the actual proportion based upon his performance. It's the same Z star as it was before. The formula is a little different here. It's P hat times 1 minus P hat over N inside the square roots. And this is just the formula for the confidence interval of this situation. We're not deriving these formulas. I'm just giving you these formulas. Okay, so what we're gonna go through today quickly is all of the different formulas for confidence intervals for all of the different situations. We have one for the mu, for the mean mu, and we have one for the proportion P. Now, of course, here for the mean mu, notice that we know sigma, correct? If we didn't know sigma, I couldn't use this one. We're going to come up with a formula today. If I do not know sigma, we're going to get to that. What if I do not know sigma? But for now, we're going to do a new one called P tilde. This is also when I'm looking for the proportion. This is also when I'm looking for the proportion P. But it's a slightly different formula. P tilde plus or minus Z star square root of, and this you're going to find on page 365 if you're interested. It's P tilde 1 minus P tilde over N plus 4. So the first thing is it's over N plus 4, not over N. That's the first thing that sometimes strikes people. Okay? The next question which you should ask yourself is what?
One more time. The P with the tilde over it, what does that represent?
Well, that's the whole question, right? The question is, what exactly is the P with the tilde over it, right? So the P tilde is equal to X plus 2 over N plus 4. And what should that lead, what question should that lead into? What is X? X equals number of X equals number of successes. So for example, if Anthony Davis shot 40 for 41, then what is X? If he shot 40 for 41, what is X? Hello? 40, right? 40 successes. What is N? 41, right? So P tilde adds 2 to the number of successes and adds 4 to the number of trials. When do we use this one? We use this one for small samples. Okay. This is when N is greater than or equal to 10. The sample size is greater than or equal to 10. but usually we use less than 30. I want to confirm that's what the book does. So hold on. Oh, yeah, I remember now. Yeah, so we use this one when n is greater than or equal to 10. We use this one when n times p hat and n times 1 minus p hat are both greater than or equal to 10. So write that down, please. So again, and we'll do examples of all of these, but what we have here is the following. We have 3 different formulas so far. The first formula is when we're drawing a confidence interval for the mean mu. In that case, it's the sample mean x bar plus or minus z star sigma over the square root of n. The next 2 examples are when we're looking for the proportion p. Now, when you take your sample, you have 2 possibilities. Either n p hat and n1 minus p hat are greater than, oh, not greater than or equal to n. It doesn't make any sense. Greater than or equal to 10, I meant to say. Are greater than or equal to 10. In that case, I would use this formula right here. And if not, but at least n is greater than or equal to 10, I would use this formula right here, where these are the, by the way, what does p hat equal to? Just to have a formula for that. What is p hat? P hat is just the sample proportion. It's the number of successes over the number of trials. The beautiful thing about confidence intervals is that you don't need to know where these formulas come from. You just have to know what these formulas are so that you can apply them to different situations. And it will always be obvious which situation is appropriate based upon our conditions. If you have the book in front of you and you turn to the front page, not the front page, but the open, the cover, then you're going to see something that we're going to use for hypothesis testing, but it's very similar. It goes through every situation and says, in this case, use this one. In this case, use this one. In this case, use this one, and so on. And when we go through all of them, it's very easy to figure out, oh, do this one in this case because that's the formula that I'm supposed to use. You plug things into a calculator and you get your answer. Okay, so we have 3 formulas so far, and we're going to do examples of them. I promise. I just want to go back and make sure I didn't skip anything by accident using the other text. But we have this, 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 we have all of this. That gets into what I was about to cover. So 16 is done. Almost. Okay. So now let's go to, well, let's do some examples before we go any further. So let me open that book again, because even though it's not our book, it's still going to have some nice examples. And let me pick out some examples from this book so that we don't got to go any further today. And we'll see it in action. Okay, so here's a Okay, so let's go through some skills tests. Let's start with number 15. It says the proportion of drivers who use seatbelts depends on characteristics such as age, sex, and ethnicity. As part of a broader study, investigators observed a random sample of 117 female Hispanic drivers in Boston. Suppose that in fact 60% of all female Hispanic drivers in the Boston area wear seatbelts. In repeated samples, the sample proportion p hat would follow approximately a normal distribution whose mean is equal to what? So remember what we did before. When we had a distribution and we said that the center had some mean and there was some deviation sigma, and then we went to a sample proportion, we said that the mean stayed the same, but now it became sigma over the square root of n. That's what we did before. When you go from the population distribution to the sample distribution, you keep the mean the same, but it gets skinnier by dividing by the square root of n. Well, the same thing is going to happen here. Okay, even though we have a sample, the proportion p hats should still follow. Where in the book does it list all the formulas? It does on the front cover of the book, it lists the one for hypothesis testing, not for confidence intervals. I will provide you a formula sheet for that one with all the conditions for when to use each one and what everything stands for. But there is no one for confidence intervals. But just like for this case here and this case here, yeah, I can do it on Canvas. I can upload it to Canvas, sure. Okay, so just like for this case here and this case here, when you do the population to the sample, the average, the expected value stays the same. Same thing here in our example. When you do the average, when you do the sample, if 60% of all female Hispanic drivers wear seatbelts, then my proportion is also going to be it's going to be the same value. It's going to be B, because the sample matches the population when it comes to the average. But the next question is, what about the standard deviation? So this one, I have to give you this formula, which I gave you before. We know that the margin of error, excuse me, the margin of error for the X bar case, it was X bar plus or minus Z star sigma over the square root of n. Now we have p hats plus or minus Z star square root of p hats times 1 minus p hats over n. So just like this guy here is the standard deviation for the sample distribution, this guy here is also the standard deviation for the sample distribution when we want a proportion. Okay, they're very symmetrical. Here's the sample mean or the proportion mean. Here's your Z star in both cases. And then we multiply it by the standard deviation for the sample. So when it says, what is the standard deviation of the distribution p hats? It's going to be p hats times 1 minus p hat all over n. Now, what is p hat in our example?
0.6.
Our p hat is not 0.6. Hold on one second. I can't. Is it possible? Yeah, I'm going to upload a chapter for all the important formulas. Okay, I promise. Okay, especially because I went a little out of order. I will make sure to include them. Okay, so here's the thing. P hats we expect p hat to land right in the middle. But p hat itself could be anything depending upon the sample. Correct? I feel like I've lost you, and I feel like that's my fault for going a little out of order. So here's what we're gonna do. We're gonna stop here a little early. We're gonna pretend this part didn't occur. I'm going to relook at everything, make a page, upload it on Canvas with all the important formulas and ideas and concepts, so that we can go over it quickly next time and catch up, because that was my bad. I thought that the book I was using was the book you were using, and therefore it was aligned perfectly, and it's not. No, it is my fault. I should have known better. I should have checked. So that is my fault. But we will go over the stuff, go in order, make sure you guys are on the same page, because I feel like it's a little wishy-washy in this stage. So let's just ignore what we're doing right now. The first part of today you still have to know, though. Right? The first part of today, which was about practical issues with confidence intervals and hypothesis testing, that is still things that you do have to know 100%. But the other stuff, we will go over it again. Okay, so what did Giovanni say? What did he do? Oh, yeah, a long time ago, right? So yes, thank you. I mean, I had the book all along. I just always thought the one online was the same one. So that was my bad. But we'll go through it. We'll get back on track. Hopefully it'll make sense. We'll keep going. So we'll stop here early today. I'm going to stop recording. April,